technical, so I need your attention, or rather uninterrupted attention, okay? So because there are lots of technical things, I'll be challenging your physics, which has been taught to you in grade 8, yes, and then what has been reinforced in grade 12, I'll be challenging that, and then we'll apply to the physiological concepts. These are the objectives. Bismillah. We'll talk about these. I just want to talk about the eyeball. Okay? The eyeball is fixed in a socket, and this socket, the eye is covered by 3 layers, and those 3 layers are important. If you look at the 3 layers, why these 3 layers are important, and the outermost layer, which is known as the tunic layer, the sclera and cornea. 1/6 of this layer is cornea, and this is the most important part because it is transparent. And the rest of the, if I say sclera, it is very tough layer. It is there to supply, to protect the internal delicate layers and cells present inside. Then the next layer is the middle layer, which is the vascular choroid layer. And this choroid layer has got a muscular part, we call it ciliary body. And there is a pigmented fibrovascular tissue, we call it iris. We have different colors of green and blue and black and different colors. It is because of this iris. And the innermost layer, which is the nervous tunic or layer, called the retina. So 5/6 part of this whole, we can say the globular part of the eye or eyeball is comprised of the retina. So this is the last, this is the most sensitive part, and this part is very important. If you just, leave that part and let's focus on, from the physiological point of view, onto this lower image. We have the anterior pole and the posterior pole. If we divide eye into 2 equal halves, it will be dividing, going through the anterior side of the eye from the cornea and dividing equally into posterior half. This is known as the equal half division of the eye, but this is not, it does not have any physiological significance. From physiological point of view, if you divide this eye into this part, which is the visual axis, and this visual axis will divide eye in such 2 parts that it is reaching to the part, we call it fovea centralis. So if any line which passes to the fovea centralis, this is the part which is very important. And this part, because this will divide all the rays of light, parallel rays of light coming into our eye, it goes and meets and forms the image at the fovea centralis. So fovea centralis is from the physiological point of view, it is the visual axis. We call it visual axis. So we are not interested into dividing eye into right and left or equal halves. We are, from physiological point of view, we are interested in dividing eye into a visual axis, through a visual axis, and that visual axis goes into the fovea centralis. Am I very clear here? Refraction. When I look my image in the mirror, what is the phenomena there? Reflection. And when a transparent media is there, then the image is refraction. So that you understand the difference between reflection and refraction. Okay. Look at the refraction is only possible if we have the 2 surfaces, or 2 media, I should say, and those media are different in their density. The parallel ray of light, this is the air is here, and this is the glass, for example. If the parallel ray of light is coming from the air and it strikes onto the glass, so we have 2 media here, interaction of 2 media. So the moment it strikes the glass, if you look at this image, so we have these parallel rays of light, and this is the glass. So parallel rays of light, when it enters the glass, enters the media perpendicularly, making a 90-degree angle. So there is no change in path. The path does not change. It goes straight, because it is making a 90-degree angle, so the path does not. It is refracted, but the path does not change. Please remember that. But when the parallel rays of light passing to the eye and making certain angle other than 90 degree, then it changes its path. It changes its path, and this is how you can see, because it is changing its path, and it is the path changes. The changing in path is, if it is entering from the lighter media to the denser media, it will move towards normal, towards the 90 degree of the media in which it is entering. And if it is entering from the thicker media to the lighter media, it will move away from the normal. So this is, what you need to understand, and this is how it can be exhibited here. So these are the parallel rays of light. If I say light, I am saying the packets of photons. This is light, okay? So these packets of photons, these lights are entering into the media, and they are making certain angles. That's why you can say there is a refraction. So the refraction depends on two factors: degree of angulation, at which angle it is entering into the surface, and the difference in the refractive indices of the two media. What is the refractive index of the media in which it is traveling and in which it is entering? So what is the refractive index? What can anybody tell me what is the refractive index?
Maybe the angle that is formed with the angle between the media.
No, refractive index. Refractive, yes, please.
Can you show how much it will bend? Like it will be
No.
It's the density of the two medium.
It's the density of two media, but it is, when the ray of light is passing, the velocity of light is 3 into 10 raised to the power 8 meter per second. Is that clear? So when the when the light is passing through a media, because of density, the velocity of light is affected. If it is passing through the vacuum, or air, or glass, or water, so the velocity of light differs. So the difference of the velocity of light in the two media which we are comparing is known as the refractive indices. Make sense? So this is the refractive index, the ratio of speed of light in the air or a vacuum, C, compared to the speed of light in the substance. If the substance is glass, if the substance is water, so we can compare the speed of light in the two media, and then you can calculate the velocity of the refractive index. Am I very clear here? Okay. We have discussed these things. What in this picture, what you need to understand is, you can see that the velocity of light when it is in the air, when it is going into the in the transparent substance, the velocity of light changes because of the density of the substance of the glass. Make sense? And we have 750 nanometer to 380 nanometer. This is our visible spectrum of wavelength, and the rest we don't know. So we are very weak on this planet, looking at very small, narrow spectrum of light. Let's talk about the types of lenses, because this is important and you will be having these things. I'm talking about the lens, not the glass. So be very clear with me. When I'm talking about the lens, we have the two biconvex. This is one convexity of the lens. This is another convexity of the lens, so it's the biconvex lens. Actually, these are part of two spheres. This is a part of another sphere. The two spheres we have cut in such a way that we have made a biconvex lens. Am I very clear? So this is a part of a sphere, we have cut it. This is a part of a sphere, we have cut it, so it's a biconvex. Plano-convex, again you can say one side is plane. The positive meniscus is this, and the negative meniscus is this, you can say, and plano-concave and the biconcave. These things are very simple. But this is what we call as a cylindrical lens. A cylinder, when a cylinder is there, when a ray of light passes through the cylinder, it makes a line. It focuses on a line, and that is what we call as a cylindrical lens. Am I very clear here? So try to understand. And we will be using the cylindrical when we do the correction of the lenses. So please remember this, okay? It is important. Now let's look at this image. Now we are talking about the lens. So we talk about the parallel rays of light coming from the infinity distance passes through this lens, biconvex lens, okay? If I look at this ray of light coming from infinity distance, it strikes the light perpendicularly and it does not change its path. Am I very clear? But look at this light, it is making certain angle here, and except this ray of light, all the rest of the rays of light are making certain angle when they enter into the glass. Once they entering into the glass, they are making certain angles, that's why they have to change, they have to refract. And because of refraction, they meet at a point behind the lens, and this is known as focal point. Am I very clear? So focal point is the distance between, if I just, look at where the dot is, red dot is. This red dot is known as pole of the lens. What we call it? This is the pole of the lens, the central part of the lens. So the distance from the pole of the lens to the point where all the rays, parallel rays of light emerging and meeting behind the lens, this is known as, so the distance from here to here is known as focal length. And this point is known as principal focus. Am I very clear here? So principal focus is the parallel rays of light, when they pass through, refract from the biconvex lens, they meet at a point which is known as principal focus, and that principal focus is important. And this principal focus, if I make a whole circle of this lens, if I make the whole circle of this lens, actually this principal focus is the center of the lens, of the sphere. Am I very clear? It is the center of the sphere. Similarly, by convention, the biconvex lens is known as converging lens, because the parallel rays of light, they converge behind the lens at a point. So this is known as biconvex lens is known as converging lens traditionally. The parallel rays of light, again, look at this point. This ray of light is falling perpendicular to the surface of the optics or the lens, and it is not changing its path. But rest of the parallel rays of light coming from infinite distance, they are making certain angles when they enter into the glass, so they are refracting. But the problem is, if they are refracting and they are making an angle, remember, when I say it is refracting, but it appears that if I draw a line from here, starting from here, then it will appear that they are refracting from this point. So this will also refract to this point. So they appear that they are diverging from a point. They are actually diverging from this point where this point is. If I draw a dotted line to all these rays, they are appearing to diverge. So by convention, the biconcave lens is known as a diverging lens. So we have converging lens, and now physiologically we talk about the converging lens or diverging lens. Am I very clear? Make sense? Converging lenses are, by convention, are positive lenses, and diverging lenses, by convention, it is a negative lens. Am I very clear? Let's focus on to this. Look at this line. These parallel rays of light. Parallel rays of light, when they are coming from infinity distance or coming from 6 meters or 20 feet, they are the same. Either they are coming from 6 meter or beyond 6 meter. Beyond 6 meter means they are coming from infinity, or within 6 meter means they are not coming from infinity. So that is the principle of calculating the visual acuity. So why we take 66 over 6 or 20 by 20? Because any parallel ray of light coming from infinity distance or coming from 6 meter or coming from 20 feet is considered as coming from infinity. Make sense? Look at this. So there is a parallel ray of light coming and it is diverging here. This is the focal point here. The parallel ray of light which is coming from infinity distance, you look at that. It is as if coming from point source, but it appears it has a focal point here. This has a focal point here. What is the difference in the focal point of the three lenses? Have different focal points and different focal lengths. Are you with me? And if you just look at this, the thickness of the lens. The thickness of the lens, the more the thicker the lens, the less the focal length. The thinner the lens, the more the focal length. Are you with me? Remember this principle. How do we know the power of a lens? We can calculate the power of a lens, and this is very simple. So the power of a lens is known as, we call it dioptric power. So power of a lens is the formula is refractive power of a convex lens is 1 over focal length in meters. Look at this. This is 1 meter distance from pore of the lens to this point. So if I want to calculate the power of the lens of this lens, so this is 1 meter distance from here to here. So it is 1 over 1. It means it has 1 dioptric power. It is how many meters? 0.5 meters. So we call 50 centimeter or 0.5 meter. So it means it has 2 diopters. 1 over 0.5 means 2 diopters. Make sense? 1 over 0.10 means 0.1 means 10 diopters. 10 diopters. Make sense? So you can understand the dioptric power. The more the globular the lens is, the more the dioptric power it has. Are you with me? Make sense? The more the globular, the thick the lens is, the more the dioptric power. The less focal length means more dioptric power. Less focal length, more dioptric power. See, the focal length is 0.1 here. Look at this lens, but its dioptric power is 10. The focal length is 1 meter, the dioptric power is 1. The focal length is 0.5 meter, the dioptric power is 2. The more the thicker, the smaller the focal length, the bigger the dioptric power. Make sense? We come across a lot of refractive indices or media, changes in media. If I just look at a ray of light coming from infinity distance from here, it strikes the cornea. Am I very clear here? Then comes into the aqueous humor, anterior chamber. Then passes through the lens, the anterior surface of the lens, then the substance of the lens, then the posterior surface of the lens, it emerges. Then it goes into the vitreous humor. And then it strikes onto the fovea centralis. Are you with me? So there are lots of media a parallel ray of light interacts with, crosses here. The first media interaction is, or it crosses, interfaces we can say. So first interface is the air, the parallel ray of light is in the air, then it crosses the anterior surface of the cornea. So this is the first interface, okay? Then we have from the posterior surface of cornea, then it enters into aqueous humor, the second interface. Then from the aqueous humor, it enters into the anterior chamber of the lens, anterior part of the lens. And then it travels into the lens. Then it goes emerges from the posterior chamber, or posterior part of the lens, goes into the vitreous humor. And finally, it strikes the fovea centralis. Am I very clear? So we have 4 we can say interfaces where the ray of light is changing its speed of light, depending upon the refractive index of that particular substance, difference of refractive index. Am I very clear? If you just look at this, air has the considering vacuum and air has one refractive index and it crosses the cornea. So the change in refractive index is 1 to 1.38, yes? And then look how much change is there, 1.38 change is there, make sense? From the cornea to aqueous humor, it is 1.38 to 1.33. How much change? 0.3? 0.0? Remember that. And then from the aqueous humor to the lens, how much? 0. 0.07. Make sense? And then from the lens into the vitreous humor, how much? Okay. Maximum change in interface takes place at which at the air cornea interface, and that is why maximum bending takes place right there. The more the interface, the more the bending will be there. Make sense? Is that clear? Any question here? Because of the maximum interface, and the difference is 0.38, where the rest of the cases 0.3 or 0.03 or 0.06 and 0.04. So you can say the maximum interface where maximum refraction takes place when the ray of light enters from air into the cornea. It means we have lots of surfaces in our, interfaces in our eye. And let's do one thing. So we have interface of air and cornea and aqueous humor, lens and aqueous humor, and then lens and vitreous humor. All these at anterior posterior make sense. So these are the four interfaces are there. And every time the ray of light is changing its velocity of light because of the densities, difference of densities or refractive index. If we remove all these interfaces and replace with one lens, the power of that lens should be plus 55 diopter. When I say plus means which lens I am talking about? Concave or convex? Convex, thank you very much. Remember that? So that the dioptric power of that lens should be, if we replace all the refractive indices or media and then remove it and take one lens, replace with one lens, we call it a reduced eye concept. This is a concept of the reduced eye. We are replacing all these refractive indices with one lens, and that lens should have a refractive power of 59 diopters. Am I very clear here? Make sense? And this is this, see, anterior surface and posterior surface because of the cornea, and cornea is the maximum refractive which is taking place. That's why there is the anterior surface has positive 48 diopters, the posterior surface has negative 4 diopters, and the lens of the eye has plus 15 diopters. So the total, if you take the minus, it will come up 59 plus 59 dioptric power. So we can replace eye with all the refractive powers or the indices of the surface interfaces by one lens, and that lens should have the dioptric power of plus 59 diopters. Make sense? Is that clear? So eye is the camera, similar to camera, because iris are the colored annuals of the radial muscles, and then we have pupil, which is the aperture of the lens or the camera. So film is where? The retina, where the image is being formed. So image is being formed in the retina, so retina is considered as the film here. Now this is the technical part. I just want to take your attention here. I'm looking at this image. There are lots of ray of light emerging from this image and coming into my eye. Yes or no? Ignore all the rays of light coming from this image. Take two rays of light. One is coming from the bottom, one is coming from the top. Are you with me? So this ray of light coming in my eye, yes? This ray of light coming in my eye, it is making an angle. This is known as visual angle. So this is a visual angle. What is visual angle? The angle subtended at the eye, taking two images, two rays of light off that image, coming from the top and coming from the bottom, ignoring the images coming from in between. So this is making this is subtending an angle in the pole, at the pole of the lens. We call it visual angle. Are you with me? Look at this. Now we are applying the visual angle to make a Snellen's chart and to define visual acuity. So I want to be, if you don't understand visual angle, tell me, because we are moving to the next concept. Look at this E. Are you looking at this E? You are looking this E also? This E is, this E and this E and this E placed at 6 meter or 12 meter or 18 meter is subtending the same visual angle. Are you with me? But the size of E is different. The size of E is different. The bigger size of E is away from the eye. The smaller size of E is close to the eye. It means if you change the object size and place it away from the eye and bring the smaller object and close to the eye, the angle subtended could be the same. So angle subtended the eye, the visual angle, depends on the distance of the object and the size of the two things. It depends on two things. It depends on the distance and it depends on the size of the object. And you can, I mean, if you want to keep the same visual angle, then you have to adjust the size. Put whatever the size is, you have to adjust the distance from the eye so that you can make a same angle as we are making it here. If this eye is brought here, it will have subtend different visual angle. Are you with me? Make sense? Okay. Don't go into this. This is not needed. I'll just focus on to this part and then we'll come back here. Okay? So let me focus here. This is a square. Are you with me? 1, 2, 3, 4, 5. A, B, C, D, E. Are you with me? Okay. So this, whatever the image is being formed, whatever the image you take it, it is subtending the same visual angle in its length and in its width. So if I just look at this E is subtending the same visual angle for its length and for its width, because it has divided into 5 boxes, and those boxes are subtending certain angle, and this is the degree, 1 over 360 turn and 1 over 60. So this is the unit of the angle subtended at the eye. You don't have to remember this, but remember that. Okay. So Snellen charts, there are two types of, if you talk about the visual acuity, let me define visual acuity. Visual acuity is the, in simple English, acuteness of vision. What is visual acuity? Acuteness of vision. Or it is the resolving power of the eye. It is the resolving power of the eye which can separate 2 points as 2 separate points. Suppose if I take a pen and put a dot here on this screen, and with the same pen I put a dot very close to it, you will appreciate the dot here, but if you are away, you will not appreciate the dots. Means the minimum separable resolving power of your eye, it depends on the distance. Make sense? So minimum separable is not, so visual acuity is the resolving power of the eye where you can separate 2 points as 2 separate points. Are you with me? It means the image of those 2 points are made as 2 separate images. If it is merged, it will be one image. So this is visual acuity. Acuteness of vision. Make sense? So it is expressed as the reciprocal of angle is subtended by 2 stimuli at the nodal point of the eye at which they recognize. This is what I have explained to you. I'm going to this part. Look at the E. The E, that letter E is written in such a way the thickness of the letter subtends one visual angle. And the whole length of the letter is subtending 5 visual angles. Whole width of the letter subtending 5 visual angles. Are you with me? So the thickness subtends 1 visual angle and the length and width subtends 5 visual angles, because we are making this in a box. Are you with me? This is the basis how Snellen's made this chart, and this is known as Snellen's chart. Acuteness of vision or visual acuity can be for 2 visions, for near vision and for distant vision. And they are, for near vision, there is a chart we call Jaggers test type chart. And for distant vision, there is a chart we call it Snellen's chart. It is based on to the principle how the visual angle is being subtended. Are you with me? So the near vision is Jaggers test type. Distant vision is Snellen's chart. Visual acuity can be calculated for a normal person. Suppose a letter E is, big letter E is made and it is placed at 60 meter distance, and you calculate the visual angle. And then a small letter E is made and it is placed at 36 meter distance, same visual angle is being. And then same E is placed at 24 meter distance. The size of the E is decreasing and the distance is also decreasing, but it is subtending the same visual angle. This is the principle. Okay? So it means the 7th line is at 6 meter of distance and 8th line is at 5 meter of distance. Are you with me? Make sense? How many lines are there? So there are 8 lines, but here in this chart there are 7 lines. So there could be 8 lines. Now look at this. Visual acuity can be calculated, and there is a formula for that. And formula is very simple. A small d over capital D. What is? Visual acuity is small d over capital D. A small d is the distance at which the characters are read, means where you are standing. And capital D is the distance from where the normal eye sees that letter. See, when you go to the optometrist office, you don't have a luxury of 60 meter long and he will put letter E there and he will ask you to see. So that's the reason we have to devise this method. V is small d over capital D. Small d is the distance where you are standing. Capital D is the distance from where the normal eye, you are comparing the normal eye which has seen this letter from which distance. So suppose you are standing, we are doing the visual acuity. So I have to do one visual acuity at a time. So for one eye at a time, and one visual acuity at a time means for distant vision or for near vision. So we are doing the distant vision. So I have to close my eye, the letter E is there, and I can read all these letters. I can read all letters standing at 6 meter distance. And I have read last letter E, last letter which is given here, N, U, A, Z, N, F, D, T. Are you with me? So this is the line I have read is standing at 6 meter distance. It means the visual acuity, I can see what a person has seen from 60 meter distance and 36 meter distance or 24 meter distance or 18 meter distance or 12 meter distance or 9 meter, but it's standing at 6 meter. And if one of you can see read the last line, it means your visual acuity is the best, excellent, because the normal person reads this letter from 5 meter distance, you are reading this letter from 6 meter distance. So visual acuity is known as, is said to be 6/6 or 6/6. Okay? So this is the 6/6 or 6/4. Suppose, now look at the scenario. I am doing for visual acuity for the right eye for distant vision, but unfortunately I cannot read A, which is there, which normal eye reads from 60 meter distance. So what is the problem? Poor visual acuity. Okay? But on the left eye, from the left eye I can see all the letters, read all the letters, see and read all the letters. So my visual acuity is normal for this eye. But for this eye, what is my visual acuity?
6/60.
No, I cannot read that. I cannot read from 60, which normal eye reads from 60 meter distance. So this is not my visual acuity. It cannot be 6/60. If I read the A with my right eye, and if I read all these letters with my left eye, the visual acuity for my right eye for distant vision will be, if I read 6/60 for right eye for distant vision and 6/6 for left eye for distant vision. Suppose if for the right eye, now I'm asking you, you have to be clear. Doing visual acuity for my right eye, I can read A, which is 60 meter. I can read D and E, F. But I cannot read H, Z and P. What is my visual acuity for the right eye for distant vision? 6/? Thank you very much, because I have read that. I haven't read H, Z and P. If I read Z and try but cannot say the other two, then it means this is not included. So my visual acuity for the right eye for distant vision would be 6/36 or 20/120 feet. Make sense?
Yes.
Are you with me?
Yes.
Please remember that.
Doctor, I have a question.
Yes?
For you, do you prefer using the metric system or do you prefer using
That's why I put this slide so that you, whatever. In America they use feet. In British system they use meters. So in Saudi Arabia they use meters. So? Yes, so that's why. In Pakistan they use meters. So, but I have, for your convenience, I have put the feet also. Now try to understand. I cannot read A, which normal person reads from 60 meter distance. What is my visual acuity? With the chart you cannot say, because I'm not able to read A. So what you have to do, you'll ask me to move to 5 meter. Now my D, small d is 5 meter. Now I can read A. So my visual acuity for the right eye for distant vision will be 5/60. Thank you very much. Unfortunately, I cannot read it at 5 meter. So I'll move to 4 meter. If I cannot read 3 meter, then 2 meter, then 1 meter. Alhamdulillah, I can read standing at 1 meter distance what normal eye reads from 60 meters. So my visual acuity for the right eye for distant vision 1/60. And if unfortunately somebody does not read A standing at 1 meter distance, is blind. So you have to, you have to come up with it. You cannot say the person is blind. You can look at this chart and say, then the person is standing at 6 meter distance, then you will start by showing small objects, counting fingers. Show them fingers. How many fingers are there? So he will say 3, 2, correctly identifies the number of fingers, then you can say that yes, his or her visual acuity for distant vision for the left eye or for the right eye would be up to counting fingers. If unfortunately the person cannot count fingers, then you will still standing at 1 meter distance. Ask hand movement, big object, which direction? Cannot appreciate, then take light perception. If person perceives light, then you can say his visual acuity for that eye for distant vision is up to light perception. If a person cannot perceive light, this is known as no light perception. This is known as, there is no legal blindness. This is total blindness. Legal blindness, legal definitions varies from different states of United America, or different states and different countries. Every country has its own legal definition of blindness. Not total blindness, please be very clear. So total blindness is defined here. Legal blindness, why legal blindness differs from country to country? Because it is involved in compensation of people who lost their vision during work. So in order to give the compensation, every country defines their own legal definition of blindness. Not total blindness, be very clear. Am I very clear? Make sense? So there is a WHO criteria, and this is the International Classification of Disease for distant vision impairment is classified as mild is 6 over, worse than. Guys, I want your attention here. When I say worse than 6 over 12 means what he has read. Thank you very much. So moderate blindness, impairment and blindness is 6 over worse than. Means he has read. Please remember. Severe is 6 over 60 means he has not read this. Legal blindness, different states have different definitions, and total blindness is no light perception. I hope this is clear. Is there any problem in this slide? Thank you. Now we are talking about the errors of refraction. We have physiological errors of refraction and we have the pathological errors of refraction. We'll take one by one. Let's talk about the physiological first. We talk about spherical aberrations. Parallel rays of light passing through the peripheral portion of the eyes do not focus on the same point actually. They're not focusing on one point, if I say. They're focusing at different points. So this is known as spherical aberration. What it is? Chromatic aberration. When a ray of light passing from the prism, a white ray of light, it divides into violet, indigo, blue, green, yellow, orange, red, 7 colors. Okay? This white light comprises of different wavelength of 7 colors. Yes? And different wavelength passes with different refraction. So that's the reason when a refractive power of a lens, this is a lens, it acts as a prism. When a white ray of light passes, it meets at different wavelengths because of the different wavelength. Because when white light passes through the lens, it divides into colors. That's the reason this is known as chromatic aberration. These are physiological refractive issues. Then third is known as diffraction. Bending of light rays as pass over a sharp borders. So this is diffraction. So these are the 3 physiological effects. And we come across this. If you look at the pathological errors of refraction, under normal physiological conditions, parallel ray of light, when it passes coming from infinite distance, it should focus on fovea centralis, should form image on fovea centralis. Okay? So, if the image is formed before the fovea centralis or after the fovea centralis, image will not be perceived. Because the photoreceptors are there. And the photoreceptors perceive the image is formed. They are stimulated, they form the image. We'll talk in the next lecture tomorrow, inshallah. So look at this. There are some issues related to that. Look what is happening here. This is known as the emmetropia or normal eye. The parallel rays of light coming from infinite distance, they focus onto fovea centralis. So we have a normal image. We call it normal eye or emmetropia. This is the condition we call it hyperopia, and this is the condition we call it myopia. What happens here? The parallel ray of light, they are forming image but behind the retina. So it will not be perceived. So we have to place it we have to give a corrective lens should be inserted so that we can bring it onto the fovea centralis, onto the retina. So that's why you have to bring the biconvex lens, okay? And in hyperopia, and sometimes in MCQs we use hyperopia or hypermetropia, please remember. And this is far-sightedness. Can you explain in hyperopia or hypermetropia, far-sightedness means what? You can see near images or distant images? You can see, thank you very much. This is sightedness, not less. Be very clear. This is far-sightedness, not far-sightedness. So be very clear. So you can see far images. So in order to provide you what you have to do? You have to give, please remember. Myopia, near-sightedness, means you can see near images, but you cannot see far images. So you have to give bicon. So the lens which is given to people, it has minus dioptric power. It means a person is myopic. So you will be giving, the optometrist will give you this lens. Make sense?
Yes.
What is happening here? Maybe look at the shape of the, thank you very much, shape of the eyeball. The shape of the eyeball is short. So definitely the image will be formed behind the retina. If the shape of the eyeball is, then image will form in front of the retina. Or if this lens is too powerful, image will be formed in front of the retina. Too weak. So there are many changes in the structure which may result into not image form onto the fovea centralis, either in front or behind. Make sense? Astigmatism. This is an important concept. Astigmatism is sometimes, it is considered that the cornea is a smooth part of the sphere. Are you with me? If because of some damage, some part of the cornea we are subject to wear and tear. If the cornea is damaged, so what happens? So parallel ray of light, if there is a depression in the cornea somewhere here, okay? So there is not it's not a smooth surface. So suppose there is a depression here. So parallel ray of light coming from infinity, it will have a different, it will go into different direction, it will go into different direction, and it will not go into the same point, it will not make to the same point. So in such cases, what you need to do, you need to put a cylindrical lens so that the image is formed onto the same, or cover this cornea with a contact lens to make it smooth. Make sense? So this is the I mean, like a clock. So these are the different planes in which the cornea is affected. So because of that, the optometrist will put a cylindrical lens, and this putting of cylindrical lens in this axis will correct the astigmatism. Am I very clear? This concept is important. When I say important means, you understand. Accommodation. I want you to focus here in these two pictures first. You are looking at distant object. Look at the lens, thickness of the lens. And all of a sudden you look at near object. Are you with me? Look at the lens and thickness of the lens. It becomes more globular. It is thin here. So this is accommodation. If you're looking at distant object and all of a sudden you're looking at near object, you are accommodating. Your lenses are accommodating. They are changing their refractive power in order to put the image onto the retina so that you can see it. Make sense? So the young children, they have refractive power of the lens they change voluntary from 20 diopter to 34 diopters, means they have 14 dioptric power of accommodation. They can accommodate, and this accommodation is important, and that is because of that they do not have difficulty. As the age advances, the accommodation power decreases, changes, and that is the reason accommodation decreases with age, and this is the condition we call it presbyopia. What is presbyopia? Biopia? When the accommodating power of the lens decreases. So you lose the power of you cannot adjust distant near objects. That's the reason you have to read the reading glasses. Am I very clear here? There are changes. This is important. Remember the cranial nerve involved here. 3 changes takes place when we are accommodating. Increased refractive power of the lens from distant to near vision. Yes? Yes or no? So oculomotor contracting ciliary muscles under control of parasympathetic nerves. Make sense? Remember that. Convergence of the eye. You are looking at distant, you are looking at near, so your eyes converge. So this ensures the rays are falling on the corresponding part of the retina. Visual axis, remember that. So this is the oculomotor nerve. Constriction of the pupil. Meiosis reduces spherical aberration, increases the depth and focus, reduces the amount of light entering into that because you have to control, and finally contraction of the sphincter muscles, again oculomotor nerve. Okay? Make sense? So these 3 changes are taking place in accommodation. Look at this, what is happening in accommodation? Now try to understand, there is a catch here. And if you don't understand this catch, your MCQ will be wrong. So try to catch the catch. What is here? Objects can see clearly only when they focus onto the retina. This is very clear. For looking at the far object, ciliary muscles are completely relaxed. So ciliary muscles are relaxed. Look at the ciliary muscles. When the ciliary muscles are relaxed, the zonular fibers which are at the lens, they contract. So these fibers are contract. When the muscles are relaxed, this catch is important. When the muscles are relaxed, the fibers are contract. So it will pull the lens, and the lens will become thin. Okay? So if I'm looking at distant object, my ciliary muscles are relaxed, but the zonular muscles are. So what happens? It will my lens will be thin. Make sense? If I'm looking near objects, the opposite will be there. I have to make the lens globular. So I have to, ciliary muscles should be contracted and the zonular muscles should be relaxed. So the lens will become globular. When you are looking at, now my question to you, if you understand this concept, you will answer this question. If you are reading or looking near objects, you will be under strain, or when you are looking at horizon, your eyes will be under strain. Near object. If you are looking at horizon, your ciliary muscles are not working. Here they are working. So that's the reason. You're looking for the horizon for hours will not strain your eye. But if you're reading, doing things, it will make your eyes difficult. Make sense? There is a concept of far point and near point and range of accommodation and amplitude of accommodation. I'll talk about that. When we were kids, our mother used to say, we are reading storybooks under the blankets in old days. So we used to read it like this. There is no light and there is no proper things. So mother used to say, don't read close, don't put the book close to your eyes. So we have to, because there is, for near point there is about 12 inches or 25 centimeter or 10 or 12 inches are the near point. This should be the minimum distance. And the for far point is 20 feet or 6 meter distance. Make sense? And the range of accommodation is the distance between the far point and the near point. And amplitude of accommodation is the difference between the refractive power. So this is what we have already talked about. Okay? You have noticed your grandparents. They used to look at this, what is happening here. As the age advances, the far point, see the near vision is increasing. Here it is, these are in meters, please remember. This is the age increasing and this is the amplitude of accommodation. What is happening here? When they don't have their glasses, they put their newspaper away from them to read it. Because the near point recedes. Make sense? Look at this, from 0.07 meter to 1 meter. They have to put it away so to read it properly without glasses. Make sense? And this is known as presbyopia. I've already. My last 2 slides, and that's it. This is my last 2 slides. Aqueous humor. Eye has a shape. Eye has a pressure. Eye is like a ball. And it is like a ball because it has to produce certain fluids into it. And the fluid produced in the anterior chamber is the aqueous humor. Aqueous humor is produced here in the ciliary muscles. Okay? Please remember these are the ciliary muscles. And these ciliary muscles are at the corner of the lens and the iris. Cornea. This is the we can say iris and lens. Here is the ciliary muscles, and ciliary muscles are producing these aqueous humor. Okay. Aqueous humor from the behind the iris and between the lens, it goes into the anterior chamber, and then this is the cornea and this is the iris. At the junction of the iridocorneal junction, there is a canal, we call it canal of Schilling. So it goes and absorbs there. Make sense? And this is a clear fluid, nourishes the cornea. Cornea does not have blood supply. It nourishes cornea. Produces ciliary muscles by diffusion and active transport. It flows through the pupil and fills the anterior chamber. That's why it maintains a pressure. Okay? It maintains a pressure. If there is a pathology, increased production, decrease absorption, the balance is not there. So what happens? The intraocular pressure would increase. The increased intraocular pressure would result into glaucoma. And the commonest reason for blindness is glaucoma. As the age advances, or does not matter, you need to check your intraocular pressure because this is the commonest reason for blindness. And how in old days we used to measure these devices, tonometers, and these tonometers are responsible for measuring the eye pressure and the pressure in the eye. When you go in the modern days, when you go to the doctor, you put your chin there, optometrist, and there is a puff of air comes to you. That checks your intraocular pressure. And then the way it goes back, and then with this theory they calculate. So the normal pressure is 12 to 20 mmHg, with an average is 15 mmHg. Make sense? In old days, we used to put, I have done that, we used to put this in wards, these tonometer and tonometer used to do that. Thank you very much. Any questions?